Hello. After this theoretical introduction with some examples, it's time for several solved problems. And in this case, solved problems will be proofs by induction. Let's start with the first one. Proving formulas, problem number 1. And this problem is pretty similar to the one we have had as an example in some of the introductory videos, right? But back then we proved a formula for the sum of 1 plus 2 plus and so on plus n. So the sum of natural numbers starting with 1 and ending with n. And here is just another formula, but the principle of proving is the same. So first let's have a look at this formula t of n. How many terms do we have at the left hand side? Well, you see that we have 1, 2, 3 and so on, and the last one is kind of numbered by n. So we have n terms in t of n, and it's one important step to realize how many terms we have so that we can produce later t of n plus 1. So we start with the base case as usually, and in the base case in this case will be t of 1, because we have here in our statement that this theorem should be true for each positive natural number, so this means that our n0 is equal to 1. And what is t1? Well, here in this formula we will just have one term. Remember, n terms for tn, so for t1 it will be one term, and this left hand side is equal to 1 divided by 1 times 2. And the right hand side, according to this formula, will be 1 divided by, here of course we have to put a question mark because we are going to prove that this formula is true for n equal to 1. The right hand side is 1 divided by, we plug in here a 1 instead of n, 1 plus 1. It's obviously true because both sides are equal to 1/2. So the base case is true. Okay. And then we can proceed and formulate the thesis for n plus 1. So for n plus 1 we will have the same start for our formula, but then we will have one more term. So we will have first 1 divided by 1 times 2 plus 1 divided by 2 times 3, and so on. And then we will have this last term for number n, so it will be n times n plus 1, but then we have to take one more term, right? Because now we are writing t of n plus 1, and this will be 1 divided by, here instead of n we have to put n plus 1, and instead of n plus 1 will give us n plus 1 plus 1 will be n plus 2. So this is what we added to the left hand side for the formula for n in order to produce the left hand side for n plus 1. This is the left hand side of t of n plus 1, and the right hand side will be n plus 1 divided by n plus 1 plus 1, which is n plus 2. So this is t of n plus 1. And now in the induction step we have to assume that our t of n is true for some n, and we have to verify if this implies that t of n plus 1 will also be true. So now assume that t of n, and it is this green formula above, is true for some n which is greater than or equal to 1. And we know that at least for n equal to 1, this statement, this formula, is true because we have verified it as the base case, right? Now we will show that this So the fact that t of n is true implies that also t of n plus 1 is true. Okay, and t of n plus 1 was this statement which I wrote in orange. So this is why I put the same color one more time. And now I will here duplicate this formula for n plus 1. And I will copy this here. So now I'm supposed to verify that this formula is true for n plus 1 instead of n, right? But I have to prove it using the assumption, the induction assumption, that this green formula is true. But the assumption tells me that this first part, so the sum of the first n terms, is equal to n divided by n plus 1, right? Because now I have to assume that the statement for n is true. So this is by induction assumption. So now I have to verify that this formula is true. This formula for n plus 1 is true, assuming that the formula for n is true. So this green part, n divided by n plus 1, is coming from the thesis for n, which we assume is true. And then I have to add to this part this last term, which is coming from the expression for n plus 1. So it will be 1 divided by n plus 1 times n plus 2. And I have to verify if this is really equal to this expression here. Well, so I have no choice. I have to compute it. So how to prove it? Well, we have to add these two expressions to each other, and these are fractional expressions, and even if they contain some variables, they should still be treated as regular fractions, right? So we have to start by finding common denominator for these two fractions. And well, it's not difficult, right? The common denominator will be the product of n plus 1 and n plus 2. So first, what has happened with this first fraction here? When we produced this new denominator, we multiplied the denominator by n plus 2. This means that we also have to multiply the numerator by n plus 2, right? And then the second one was unchanged because this new denominator was already its old denominator, so it will be just plus 1. Okay, and what do we get here? Well, let's perform this multiplication in the numerator. Then we will get n squared plus 2n, right? It's the distributive law, and plus 1, which was standing there this entire time. And in the denominator, we have this product as before. But now look carefully, what do we get in this, maybe another color which I didn't have yet, this one. What do we have here? You probably recognize the formula for the square of a sum, right? This is n plus 1 all squared, right? And in the denominator, n plus 1 times n plus 2. And we see that we have some cancellation. We have n plus 1 in the denominator as factor, and also in the numerator, because in the numerator we have n plus 1 times n plus 1. So this square disappears. And altogether we get the result, which is n plus 1 divided by, now it's an ugly line, divided by n plus 2. And you see, it is exactly what we were supposed to get. This is exactly this number which we, or this expression which we were supposed to get. So indeed we see that if we suppose that our thesis is true for some n, then this information will give us a conclusion that the same statement is true for the next natural number, which is n plus 1. And then we just write that by the principle of mathematical induction, our T of n is true for all n which are positive natural numbers, because we have proven the base case, and then we have proven that if T of n is true for some n, which is a positive natural number, then the thesis is true for the next number as well. Okay, that's all for now. Thank you for watching. Bye bye.